Welcome to lecture number 22 of my series on classical thermodynamics. In today's lecture, we will cover a topic which is usually not that often touched upon in elementary thermodynamics courses, the topic of stability of thermodynamic systems. We begin with a statement which should be very familiar to all of you by now. The internal energy, expressed as a function of entropy, volume, and number of moles of particles, has complete thermodynamic information about a simple hydrostatic system. We can turn this around and say that the entropy expressed as a function of U, V, and N also has complete thermodynamic information. Now, if the system were not a simple one, but for example one with several components with amounts N1, N2, etc., then U expressed as a function of entropy, volume, N1, N2, N3, etc., would also have complete thermodynamic information. Now this equation, U expressed as a function of SV, N or N1, N2, etc., or S expressed as U, V, N1, N2, etc., is called the fundamental equation for the thermodynamic system. And as we have stressed earlier several times, the fundamental equation cannot be deduced from thermodynamics alone. It can either be deduced experimentally by extrapolating experimental data or back calculating from experimental equations of state, or through a more fundamental theory, say statistical mechanics. Now the question that I want to address today is every fundamental equation that can be obtained in this way a valid thermodynamic fundamental equation? And the answer to that is actually no. There are special considerations that we must apply to fundamental equations before they can qualify as valid equations describing thermodynamics of a system. And these special considerations have to do with stability of the underlying thermodynamic system. Now, in order to understand what this stability issue is, let us give an example. Let us say we have a function S, and here we have just shown its variation with the internal energy. V and N for the time being are held constant, and let's say the curve describing S as a function of U as part of the fundamental equation is given by this red curve here. Now, for the region shown here between U minus delta U and U plus delta U, you can see that the chord joining the point at U minus delta U and the point at U plus delta U, this black dashed line here, lies above the curve. And if you look at what is happening exactly at the midpoint of this curve, you can easily see that geometrically it follows that the value of the entropy at U, this value, is actually less than half of S at U minus delta U plus S at U plus delta U. So half of these two values, average of these two values. Now it turns out that a system described by a fundamental equation like this would be thermodynamically unstable. And to see why, let us go back to the example that we used in the last lecture, the example of an isolated system with a wall in between. So we have a system with two subsystems on the two sides of this wall, and let's say they are both identical. They have internal energy U, V, and N on both sides, and so the fundamental equation would tell you what the entropy is on both sides. And the entropy of the overall system is the sum of the two, which is twice SUVN. Now let's just say that the wall in between is completely impervious. It's adiabatic, it's immovable, and it's impermeable. Then of course, the system would be in equilibrium as of itself. However, let's just imagine what would happen if you could move delta U amount of energy from the left hand side to the right hand side. That could happen, of course, if the wall in between were diathermal. So, S of U minus delta U Vn would be the entropy of the left hand side now. S of U plus delta U V comma N would be the entropy of the right hand side. So, net entropy of the closed system would become the sum of these two things. And if you go back to our supposed dependence of S on U, this sum would be more than twice S of U Vn. What that means is that this process of transferring delta U amount of heat, of energy, spontaneously from the left to the right would actually increase the entropy of the system. And remember, a closed isolated system, which the whole system is, would evolve spontaneously towards higher and higher values of entropy, which means that the moment you allow this wall to be diathermal, the system would spontaneously change by losing energy from one side, and that energy goes automatically to the other side. So you started with two identical states on the two sides. It would spontaneously lose energy and hence become lower in temperature on one side and gain energy and higher in temperature on the other side. Now realize that this would happen even without the wall. The wall was just an artifact here. If you did not even have the wall, what would happen is that spontaneous flow of energy would occur from one part of the system to another part, and you would end up with the system becoming inhomogeneous automatically without any external intervention. Now, this kind of spontaneous inhomogeneity developing within a system is a sign of instability. This does happen in some systems. In fact, it happens when a phase transition occurs. And it turns out, as we will see, that this kind of fundamental equation, which is not the correct thermodynamic fundamental equation, is often a signal of a phase transition that would occur in the system. So what would you need for stability? What you would need is entropy must be a concave function of energy. That is to say, if you were to take S of U minus delta U, I'm not really bothered about the other variables right now, add to it S of U plus delta U, all the other variables are of course fixed at the same value, then you must have a value which is less than or equal to twice as U, with other variables staying at the same values again. And this means that the curve must always lie above these chords, not below, as in our example that we had drawn. Now, if you take delta U to be infinitesimally small, in that limit, this actually translates to something pretty straightforward. This really tells you that the second derivative or second partial derivative of the entropy with respect to the energy at fixed V and N must be negative or adverse zero. However, this condition actually is less restrictive than the concavity condition. Note that this condition only says that you have a local maximum. If you move slightly from U in either direction, the value drops off. However, the concavity condition is much more general. It does not talk of slightly moving away from U. Delta U in this expression can be large. So, while this is a very convenient thing to talk about, the actual stability condition is given by the full concavity condition. We will soon see the reason why the difference is important. Well, the same considerations can be applied to volume changes as well. You must have S of u at V minus delta V comma n plus S of u at V plus delta V comma n being less than or equal to twice S u V n. And in fact, a similar thing would also happen with n. Now, if, for example, S were a convex function of V, what would happen is volume decreasing in one part of the system and increasing in another spontaneously would actually be favored, because that would lead to higher entropy. That is not supposed to happen. Once again, the infinitesimal version of this in the limit delta V goes to 0 is given by del 2s del V2 at fixed u and n being less than or equal to 0. We, of course, have another similar relationship for n. Now, in general, at least, when I say in general, I mean, although we are keeping n fixed, you are allowing both u and v to vary, you should have the following: S of u plus delta u, comma v plus delta v, comma n, added to S of u minus delta u, v minus delta v, comma n. This must be less than or equal to twice as u, v, n. So rather than talk about tangent lines or chords, straight line chords, lying below the curve, what we really should say is the following: the entropy curve must lie below its tangents. That's what it says here, but that actually is only when you talk about the dependence of the entropy one variable at a time. When you're talking of the dependence of the entropy on all of its variables, what this really says is that the entropy surface must lie below its tangent planes. That's exactly what this concavity condition really means. Now, this is exactly what you need to repair faulty fundamental equations and end up with thermodynamically valid fundamental equations. We are going to discuss this soon, but before we go there, let's take a look at what this expression says in its infinitesimal version. Now, you might expect that this would tell you that del 2s del u2 and del 2s del v2 are both less than or equal to 0. But there is a surprise in store for you. A surprise, that is, unless you have already studied extremization of functions of multiple variables, in which case, of course, you would know what I am leading to here. In any case, let's take a look at what the value of S of u plus delta u, v plus delta v, comma n is. We are going to assume here that S is a smooth enough function of u and v, smooth enough in the sense that it has enough partial derivatives that we need for this. So, standard Taylor expansion, which we can do in this case, tells us that the value of S with these arguments is S at u v n plus del S del u at v comma n delta u. That's the first order change because of change in u, plus del S del v at u comma n. I should have put in the u here as well, delta v, plus second order changes. And the second order changes, again, standard Taylor series, is given by 1 by 2 factorial del 2s del u2 at constant v and n, evaluated at u v n actually, times delta u square, plus 1 by 2 factorial del 2s del v2 with u and n fixed, delta v square, plus a mixed term del 2s del u del v at constant n, actually is del s del v done at constant u and n, then del u done at constant v and n, times delta u delta v. Plus, of course, there are higher order terms. Now, what about S at U minus delta U, V minus delta V? Of course, it's exactly the same expression with the signs of delta U and delta V changed, which would only change these two terms. The other terms will not be affected by that. So you are going to end up with this expression. Now, if you were to add these two expressions, you are of course going to get twice SUVN. These terms will cancel and you will get double of this term. So what you get when you subtract twice SUVN from this sum and expect that to be less than or equal to 0, that's the concavity condition, you would end up with this expression, the second order term, to be less than or equal to 0. Of course, there are higher order terms as well, but for sufficiently small delta U and delta V, you can ignore those higher order terms compared to the second order ones. Now, this is a quadratic expression involving squares of delta U and delta V and the product of delta U times delta V. Now, if this third term had not been there, this would have simply been the sum of two squares with two factors in front, and this being less than or equal to 0 would immediately translate to this being negative and this being negative. However, the presence of this mixed term actually makes life a bit more difficult. And to see this, let's just start with a standard second order polynomial of two variables x and y. Well, x and y here are just shorthands for delta U and delta V, and these coefficients a, b and c are just shorthands for these expressions. But this is of course a much more general statement than just one that we would use for thermodynamics. There is just an extremization statement for any second order polynomial and essentially one which is valid for any kind of function whose second derivatives exist. Anyway, if you start with this quadratic expression ax square plus by square plus 2cxy and demand that this is less than or equal to 0 always for all values of x and y, the standard way to tackle that would be to complete the square. So a into x square plus twice c by a xy is an expression for which the square can be completed easily by adding c square by a square y square. Of course, by square is left out here, and if you complete the square, you get a into this square plus 1 over a, ab minus c square into y square. Now, in order that this be always less than or equal to 0, given that this square and this square, y square, are always positive, what we must demand is that this coefficient and this overall coefficient both be negative. So a must be negative, and since a is negative or 0, ab minus c square must be greater than or equal to 0. Remember, this thing times 1 by a, which is already known to be less than or equal to 0, must be negative. So this is the condition you have for this square to be less than or equal to 0 always. A must be less than or equal to 0, but this cross term ab minus c square must be greater than or equal to 0. Now this might surprise you a bit, because after all, if you look at the symmetry of this expression, you would also expect b to be less than or equal to 0 to come out from this calculation. Well, that's not something we have written down here, but you must realize that if this is to hold, then ab must be greater than or equal to c square, which means ab must be positive. Since a is less than or equal to 0, b has to be less than or equal to 0 as well. So you do not need to specify b less than or equal to 0 as an additional condition. These two conditions would also imply that. Now, applying this to our example, where you demand this to be less than or equal to 0 for stability, actually local stability. As we have already said, concavity is a more restrictive condition, but it would definitely imply this. And that would automatically tell you that del 2s del u2 would have to be less than or equal to 0, and this product, second derivative of s with respect to u times second derivative of s with respect to v, minus the square of del 2s del u del v. This has to be greater than or equal to 0. Once again, let me stress that we did not say that del 2s del v2 has to be less than or equal to 0, but these two conditions together would also imply that. Now, I understand that this may be unfamiliar to most of you. So let us try to understand exactly why this term is necessary. To see this, let us go back to the expression for what the value of s is as you move away from the point u, v, n. Of course, you have the value at the point u, v, n, plus these two terms in blue actually tell you how s would have changed if you had moved along the tangent plane to the surface of s at the point u, v, n. Of course, if the values of delta u and delta v are tiny enough, the tangent plane is a very good approximation for the actual surface. So, to first order in change in u and v, this would be the value of s as u or v changes slightly. Now, what about this term in green? That actually tells you how much of a deviation would there be from the tangent plane as you move away from the point u, v, n. Well, not only this term, but higher order terms which we have just indicated by these three dots here would also contribute to this deviation. But as long as delta u and delta v are tiny enough, we can safely ignore the higher order terms when we are looking for the deviation from the local tangents. Now, let me just draw a picture which tries to depict how s changes as you change u or v. Now, this is a rather crude picture in which I have not drawn the entire surface, but I have drawn two lines. This line indicates how s would change as you changed u and u alone. So, this is actually delta v equal to 0. Similarly, this line corresponds to delta u equal to 0. This is the point u, v, n, and as you move along this line marked v, only v changes, delta u is 0. Now, if del 2s del u2 were negative and you were moving only along this line, that is the line with delta v equal to 0, then the deviation from the local tangent, this straight line here, remember we are just looking at this curve, so the tangent would be just a straight line, would be given by the term 1/2 del 2s del u2 delta u whole square. And since delta u whole square is positive no matter whether you move this way or that way, the way in which this term contributes depends only on the sign of del 2s del u2, which, if it is negative, as we have demanded, would tell you that as you move away from this point, you are going to go below the local tangent, which of course is what you want for concavity. Similarly, if you were to move along the line marked v, which is delta u equal to 0, the change from the local tangent, in this case this straight line, would be 1/2 of del 2s del v2 delta v square, delta u being 0, the other two terms in the quadratic piece would drop off, and so you would again go below the local tangent. So del 2s del u2 being negative and del 2s del v2 being negative together would seem to imply that the function is concave. At least it looks concave as you move along lines with v equal to constant or u equal to constant. However, remember that we do not necessarily have to move in just these directions. We can also change both v and u. So move in some intermediate direction from the ones given by these lines. And if the surface is fluted like this is a rather crude drawing, so please forgive me for that. it might so happen that although you are going down from the local tangents as you move along the line of constant u or constant v, as you move along some intermediate direction, the curve actually goes above the local tangent. I would urge you to imagine the shape of the surface in this case. My crude drawing may not be a very good one, but it should give you an idea about what I mean. And if you had something like this, then despite del 2s del u2 and del 2s del v2 being both negative, you would not have a concave surface. This condition essentially ensures that such a thing doesn't happen. If the surface obeyed this condition, then it would not be fluted in this manner. Then even if you were to move in some intermediate direction, you would still actually go below the local tangents. So that is what this condition really means. Let us now turn to the question of repairing a faulty fundamental equation. As we have stressed before, extrapolation from data, back calculation, or statistical mechanics may sometimes lead to a fundamental equation which do not obey the concavity conditions. And in such situations, you need to repair the equation. Now, I'm going to illustrate that through this graph here. Here we have plotted S versus X. X stands for any one of the extensive variables which are arguments for S in the fundamental equation. We are going to assume for the time being that all the other extensive variables are being held fixed. So X here could stand for U, it could stand for V, it could stand for N1 or N2 or whatever. Now, let us say our equation, the fundamental equation that we have obtained from some source, gives us this red curve for S versus X. A, B, C, D, E, F, G. Now you can clearly see that the region between B and F, this part B, C, D, E, F, is actually something which violates the concavity condition. Take any 2 points in this region and draw a chord, the curve will lie below the chord. So, here we have an unstable fundamental equation, or really a fundamental equation depicting an unstable system. Let me also stress that only in the path between C to E do you have the first derivative, the slope of the curve, increasing. So del 2s del x2 is greater than or equal to 0, while as the local concavity condition only from C to E. If you look at the region between B to C here or E to F here, in both these regions the slope is actually decreasing. The curve is becoming flatter as you increase x. That means in BC, also in EF, you actually have local stability. If you take a point, say, whose value is x0 here, and go from x0 to x0 minus delta x and x0 plus delta x, the sum of S at x0 minus delta x and S of x0 plus delta x in this case will be less than or equal to twice S x0. The entropy will actually decrease, so you will have no reason for the system to develop an spontaneous inhomogeneity in X. However, that is true only when you are talking of small changes which stays within this region. If for large changes in X, even this part BC and the part EF are unstable. So these are locally stable but globally unstable regions of the fundamental equation. Now, as we have already said, the true fundamental equation must always lie below the superior tangents. That's true at the point A. In fact, it's true at all points between A to B. It's also true beyond F. But it does not work in this region, which is the faulty region. Now, how do you repair the fundamental equation? Simple. You just keep on drawing the superior tangents. And here at the point B, you have a superior tangent which just touches the point F, this line BHF. And the actual fundamental equation will be the envelope of all these superior tangents. What that means is that the actual fundamental equation will follow the curve from A to B, then it will go straight from B to F along this superior tangent and then go from F to G. So this faulty region BCDEF will be excised out of the fundamental equation. We will see that this has a huge role to play later on when we talk about phase transitions. In fact, the straight line region in the true thermodynamic fundamental equation ABHFG, the straight line region BHF signifies a phase transition. It actually signifies that as you move along this, as you change the x, what happens is you have a state at B with a particular value of s of x. You also have another state at F with another value of s of x. And anywhere in between, different parts of these two states coexist. As a result, the S becomes a linear combination of the S here and the S here, depending on how much of the state at B or the state at F is there. So, if you're talking of a situation where water changes into steam, this would be the region where water and steam coexist, and what the entropy would have been at any given point, given value of x, which could be any parameter which you are varying along this transition, it just decides how much of water you have and how much of steam you have. So this is the final result about repairing a fundamental equation. The envelope of the superior tangent ABHFG gives the repaired thermodynamic fundamental equation. This is the correct fundamental equation according to thermodynamics. And the straight line part of the repaired fundamental equation corresponds to phase separation. This is going to be extremely important when we talk about phase transitions later. So far, we have described the stability conditions in terms of entropy expressed as a function of U, V, and possibly N1, N2, N3, and so on. Can we turn the discussion around and talk about U as a function of S, V, N, etc.? Of course, we can. Now, notice that if you have a fixed S, V, N in equilibrium, second law would demand that U has to be a minimum. And this means that the stability condition in terms of U as a function of S, V, and N would be just the opposite of the stability condition for S expressed as a function of U, V, and N. Instead of being a concave function, U must be a convex function, so that it must satisfy this condition. U with S plus delta S, V plus delta V, and N, added to U at S minus delta S, V minus delta V, and N, must actually be larger than or at worst equal to twice U, S, V, N. This will ensure that if you were to change the entropy of one part of the system at the expense of another part, or the volume of one part of the system at the expense of the other part, the energy will actually go up, and therefore such things will never happen spontaneously in a closed system. Now, as before, we can talk about the conditions which these lead to when delta S or delta V is infinitesimally small. Obviously, what this will lead to is del 2 U del S2 is greater than equal to 0. Note, greater than equal to 0. That's the opposite of less than equal to 0, as was the case for the second derivatives of the entropy. And delta U del V2 is also greater than equal to 0. These are the local conditions, of course, along the lines where you're changing S or V alone. Of course, in addition to that, you also have this condition, del 2u del S2 del 2u del V2 minus the square of del 2u del S del V whole square. This once again has to be greater than or equal to 0. This particular combination has to be greater than or equal to 0 and not reverse to less than or equal to 0. Why? I would urge you to think about what makes ax square plus by square plus twice cxy a minimum as opposed to a maximum. By completing the square once again, take a hard look at the derivation that we did earlier. You would be easily able to understand why this has to be greater than or equal to 0 and not, as you might expect, change its inequality. Now notice that in this form it's pretty easy to see that there are certain physical significances to these conditions. Del 2u del S2, for example, is actually del T del S. What that tells us essentially is that if we were to increase the entropy at constant volume and number of particles, the temperature would go up, which essentially says that the heat capacity Cv will be positive. A similar statement can be made about this. In fact, the stability conditions are very, very significant as far as physics is concerned. Not only do they indicate where phase transitions or some instabilities might develop in the system, even when the system obeys the stability conditions, they do make very important statements about physically important parameters. We will explore this as well as what these stability conditions tell us about the other thermodynamic potentials in some detail in the next lecture. Bye till then.